you hand those out to everybody? Yeah. Thanks. Ooh. All right, how is everybody? One thumbs up. Okay, who would like to start us off with a prayer? Okay, it's either John or Giovanni. Dang.
Our dear Heavenly Father, we are very grateful for this day, and we're grateful for the opportunity we have to learn from Brother Corey today. We're thankful for the lesson that he has prepared, and that we have the opportunity to come to BYU. We ask the Lord that may please bless us to be guided by the Spirit, and please bless Brother Corey, that he may be able to feel by Spirit and feel direction to know how to conduct this discussion, that we may all be able to learn and grow. And please bless us all to understand his words and this material. We say this in the name of Jesus Christ. Amen.
Amen. Thank you. You almost called me Elder Corey. Yeah. I have a son. He's in the home MTZ. He's Elder Corey. So it's like, yeah, that's who you're blessing, right? He's learning Koreans, and he needs a lot of prayer, so include him. Okay. Any comments about the devotional? So Elder Bednar talked yesterday. Yes.
I can add my testimony to one needed. I was actually one of the people who was called and got a ceiling scooted up.
Wow.
So it was pretty crazy how everything lined up, and I testify there were miracles that made sure everyone who wanted to be there could be there. Even it was incredible.
That's awesome. Which temple?
San Diego.
San Diego. Wow, so cool. Thank you. Okay. Other comments about the devotional? Okay. Very powerful and solemn. Like it's just such a, yeah. Just kind of like the tone of it was different than most devotionals, but very, very good. Okay. By the way, if you look at the ages of the members of the Quorum of the 12, Elder Bednar is about 20 years younger than all of the other members around him. It's like, unless something drastic happens, he's destined to be president of the church. So just the way the ages work out. All right. Let's pull up. Okay, quick thing about vectors and points. So you guys are comfortable with points, especially in the plane. Just one thing to illustrate the difference between vectors and points. So you could label A, B, C, D, E, F, and O there. O is the origin. Or you could label them with points. They'd all have different coordinates. I'm not projecting here. Hold on. All of those vectors are exactly the same vector. They would all have the same values. So they're two-dimensional vectors. The x-coordinates and the y-coordinates for those vectors would all be the same. Okay? They all move. They all have the same length. They all move in the same direction. So, and you could find them in any of these ways. You could take B minus A. You could take C minus O. You could take O minus F. You could take D minus E. All of those would be the same vector. You get the exact same values out for all of those. And the coordinates of those would be the same coordinates as the point C. Right? Because if you put that vector at the origin, it points to C. So sometimes we interchange points and vectors because a lot of the time we can just think about vectors as starting at the origin, and then all the values the coordinates you have for the points are the same you have for your vectors. So, but wanted to illustrate that. Any questions about difference between points and vectors? I'm still working on my explanation of the difference between points and vectors. I'm still trying to figure it out. Yeah, I'm going to come back to questions for 1.3, but this is a connection to 1.2. So I wanted to make this wooden tetrahedron. So it's a regular tetrahedron here. I know that the upper left picture there doesn't look like a regular tetrahedron. It looks skewampus, but that's only because of the direction I took the picture and then the direction that you're looking at the picture. If you hold the picture in front of you about like this, then it looks right. But that's, if you have an art background, you understand why. Or if you want to take perspective geometry, you can also understand why. But to make this tetrahedron, there's an interesting math problem that's not trivial. I mean, cutting out the equilateral triangle is pretty easy. 60 degrees, you can just cut it to 60 degrees on the table saw. But figuring out what this bevel angle is around, that's not so easy. To do that, there's actually been a problem that shows up on the state math contest every once in a while. So kind of tells you the difficulty of it. It's just not trivial. You can use the law of cosines to figure it out, but the easiest way to do it is just to use dot products. So this kind of illustrates I tried to get the best picture for the angles there, showed my table saw and my messy shop in the background there. So one strategy is you pick a length for the coordinates. It doesn't matter what the side length is, so you just pick a length, put the coordinates, pick a set of coordinates, and then you can pick the two vectors. One goes from a midpoint to the vertex, an opposite vertex on the side, and then one goes from the midpoint to the opposite midpoint. And then you have to figure out the angle between those. And the easiest way to do that is take the vector, find the dot products, divide by the two lengths, then take arc cosine, and then you've got it. It's a lot easier than what you have to do with the law of cosines. So thought you'd enjoy that. So, okay. Questions from 1.3? Okay. Why don't you start off telling your neighbor your question, okay? Talk to your neighbor about what was hard or what you didn't understand, and then your neighbor can ask the question.
Anyone here today online?
Yeah, buddy.
Hey, let's go.
Sorry, I'm being a bit of a, I don't know, like a dork with my stupid intros or whatever, but
It's okay.
How are you?
Been pretty good. Just a little bit not very good at linear algebra. That's my issue. But
Dude, I feel like no one is until you like do it.
yeah. Lebesheim was easy though, but I imagine the homework's gonna be really difficult. But Lebesheim was just like I kind of just guessed on some of them and it ended up working out. So anyways, I guess I never really knew what normal form was because I don't think we really went over that in the pre-class lecture. So when I got to the normal form on Lebesheim, that was a little tricky. So I guess
I agree. I had the same thing basically, and I was having to like look it up and stuff, and I found a video somewhere or whatever, but I still don't feel like I really have an intuitive understanding of what it's doing exactly. So
yeah, parametric form makes a lot of sense, but yeah, normal form is just kind of. I thought it was normal form was the same thing as vector form, but I guess not. So
yeah. So what is it doing exactly? It's like this gives you.
Right. So one question that was asked was, in this general form here of a line, why do you need two equations? So each of these equations is the equation of a plane. So the equation of a plane in R3 is simpler than the equation of a line in R3. To get a line, you take two planes that aren't parallel, and where they intersect is a line. So you have these two planes, and now any xyz that make both of those true are on that intersection, and that is the line. So Yeah, kind of counterintuitive because you'd think the line would be easier, like simpler than the plane, but it's not. Okay, so other questions that came up in your conversations? Yes. Okay. And your name is, hold on, does it start with an M? Molly? Okay. So what's the parameter? So yeah, here in vector form and parametric form, we have these T's and these S and T's. So, so these parameters, in most cases, we let them be any real number. We let them run from negative infinity to infinity. And so with a line, what you get is you get this point. You can pick any point and any direction vector. So that's D. And then if I have P plus TD, and I let T vary, then at T equals 0, I'm just right there. At T equals 1, I'm right here at the end of D. At T equals 2, I've got another a vector, and then T equals 3, etc. T equals a -1 would be right there. And if T can be any value, it stretches this direction vector out as far as we want and back as far as we want, and it'll hit all of those points. So one reason we use T as a parameter, because a lot of context for parametric equations uses time, like things changing over time. So you can imagine this line being drawn out over time from negative infinity to infinity. It takes a long time. So at what point is, you could give me a time and I'll tell you where that point is. So it is a different way of thinking about equations. You did touch on them a bit in 113 or Calculus 2. Well, if you had Calculus 2 in high school, I'm not sure if you did parametric equations, but here we do it a little bit. But I know it's not tons. So does that help, Molly? Okay, other questions? Yes.
I was wondering about the equation for a plane, the normal equation for a plane in R3. Why does it end up like that?
Nice. Okay, so the normal equation, sorry, pull that up, Sam. I'm just kidding now, go back to the board. I'm just kidding, let's go back, okay. Okay, so the normal form and the general form are closely connected. The vector form and the parametric form are closely connected. It's easier to see the vector form than the parametric form, because if you just take your vectors and start writing out each of the components, then you get those equations. But here, let's start talking about the normal form and the general form. So where's my eraser? So we have a normal dot x equals normal dot p, where p is some point, okay? And these are vectors. Well, the general form, we have some ax plus by plus cz equals d. We can rewrite this left-hand form, this left hand of this, we can rewrite it as a dot product. And that dot product is the coefficients, a, b, c, dot the variables x, y, z. And this x bar or x arrow over here, this x vector, it is exactly this vector of unknowns. Whether you call them x, y, z, or x1, y1, I'm sorry, x1, x2, x3, it's this vector of unknowns. And this normal vector is this equation. Is this vector. These coefficients, a, b, c, create a vector that's normal to the plane that this defines. So I talk a little bit about why in the peanut butter book in chapter 5, if you can slog through it. So the left-hand side we can see a little bit. Yeah, dot product this, you get that, and you kind of have to believe that this is, this is perpendicular. This vector, ABC, this coefficient vector is perpendicular to the plane. What about this left-hand side? I'm sorry, this right-hand side. Well, let's pick a, suppose we knew the coefficients, but we didn't know D here. What could we do to find D? Yes. Great, yeah, if we have a point, just plug in the values of the point. So if I have 1, 2, 1, let's say this is a point in this plane, then you would plug it in for, this is your x coordinate, 2 is your y coordinate, 1 is your z coordinate. So I would have 1, 1 plus 2, 2's minus 3 1's, and that would equal D. Well, what is this? So we can rewrite this also as a dot product. It still has the same coefficients, 1, 2, 3. Still has 1, 2, and a -3. It still has our ABC here. Dot 1, 2, 1. That's the point that we had. So this is still our normal vector, and this is a dot our point vector. So, and we get that in this dot product. The dot product of this vector, if we get all the points that have a dot product of that vector that equal the same value, that defines a point on, that defines a plane. It's kind of weird that it does. If you're new to this, I try to explain it in the peanut butter book. But. Okay, so this gets us our D. Does that help? Okay, so yeah, it helps me a lot to start to connect it to this one. So do the left hand and the right hand. Okay, other questions? Yes. Yeah, so X bar, yeah, X is our unknowns. So it's our X, Y's, and Z's. So it's they tend to be our unknowns. So we're capturing, like in a line, AX plus BY equals C. So you're used to this. We're just going to group the X and the Y together. Those are two unknowns here. Those are two variables, and we're thinking A, B, and C as constants. So there are two variables. We're going to group them together and put them in one vector. So we can think about them as X, Y. So. Oh, you're calling this the original equation. Okay, so the normal form. So this is called the normal form. It's saying so in parts we know what n is, we know what p is, we just don't know what x is. That's usually the way we're writing down equations, right? So it's saying it's all of the points. So all of the x, y, z's, or x1, x2, x3. This actually doesn't matter. You'll notice it's the same as. Oh, never mind. Oh yeah. So here, the normal form in R2, they could just be 2 dimensions. In R3, we get a plane. We do need to have 2 there, but so this is saying all of the points x, y, z. Or xy, dotted with this vector that are the same of a particular point dotted with the vector. That's kind of the set we're thinking about. So any xy that we can plug in and make this true, then those are the points that are we care about. And those are the points of a plane in R3 or a line in R2. So I don't know if that helped very much, but yeah, there is we are making a statement in the same way that here we say, but I never finished this one. So x plus 2y minus 3z equals, what does this end up being? 4 minus 5 minus, so it ends up being 2 maybe. Okay. When we write this down, like, we can't just plug any x, y, and z in there to make the whole thing true, right? It's the x, y, z combinations that make this true are points on a plane. So geometrically, that's the way we interpret this. So they all have this relationship. And this just gives us another way of saying, like, yeah, all the ones that make this true, if I give you a particular 1, 1, 2, x, y, z, 1, 1, 2, 3, 4, minus 7, whatever it is. So dot, dot. Yeah, all the x, y, z's that make this true, they define something, and it's a plane. So, okay, great. Other questions? Yes. Yeah, let's do that in a little bit. I want to turn you guys loose on this. Turn you guys loose on this problem, okay? I made a mistake when we got to number 3 last time, so I hope we can do it better this time. So you can work with a neighbor on this. If you have questions on this or other things, just raise your hand and I'll try to come around and answer them. So. And for those of you that are online, sorry, I uploaded this worksheet to Learning Suite. So those of you that are online, you can go to the content page that says post lecture material, go to day 3, and there's just one thing under day 3, and it's this handout. So that's what we're working on right now.
Were you guys able to find the worksheet?
I think I found it.
Okay. It has like a triangle on it, I think. Yeah. Okay.
I must not be looking at the right thing. It's
It's
not.
under post-lecture material.
Oh, there we go. Not pre-lecture. Okay, now I see it.
Yeah, it took me a minute to find. I was like, what the heck? I was just, yeah. Hmm. Do you have any idea how you do question 1?
I'm thinking about it, and isn't this the one where we do like B minus D to get the G, and then we do like E minus B, and then we have 2 vectors and a point. That's what I'm remembering. And then we would have a point plus, I don't know. This sounds like gibberish when I'm talking. I hate talking. I kind of prefer to like write it. Let
Yeah.
me I'm thinking it's where we do hold on, I gotta set it up so I can look at both of them. Do you agree with me so far, or does it make sense what I'm rambling about?
How do you get how do you get vectors?
So I think there's numbers on the axis if you look at it.
Okay, how would you get a vector out of a line, I guess? Is it just like the points, I guess? So
Yeah.
is the vector like,
You're right, it is. It would be like 2, 0, 0 for B.
so 2, 0, 0 for B, and that's a vector
Or a point.
or a point? It's either?
Yeah, like that's my understanding is it's like a vector or a point, but say we wanted to get like G, that's lowercase g up to D,
Mm-hmm.
then we sorry.
You'd use point D. You'd use point D to get that vector, I guess?
Yeah, D minus B.
Oh, D
Something,
minus B.
or something like that, or B minus D. And then it'll give you like a, if I remember right. Yeah, I hate like saying this stuff because I'm like super shaky myself. So, but that's basically how you get those vectors in between is you do point D minus point B, and now we have lowercase g. You see what I'm saying?
Yeah.
And then we're supposed to be able to do something where we're like, where we can, it's like point plus S. I don't know. Do you see what I put in there?
Yeah. Point plus
know.
S vector plus T vector.
You remember when we were doing that?
Yeah. Okay. So
what I'm thinking is we would have something like E plus you know, G. Oh, crap. I forgot how to get the S and the T though. Oh, well. But it would be E plus G plus, and then like K, and then I forget how you get S and T, something like that.
It's like a scalar, right?
Yeah, and I can't remember what you dot product to get it or something.
Mm-hmm.
What is it? Oh my gosh, dude. Is it like, ugh, I feel like I just need to go review something. Oh, well. But yeah, that's basically how I think we would do it. We would figure out, you know, we would get 2 vectors and a point. Let me see if I can find it real quick. I guess if we're just working on it.
Here, let me pull out my paper. So the vector that defines D is D minus B. It's hard for me to see the numbers on D. Like, is that 0.5 and 3? And then 0?
I don't know. To me, I think it's 2, X, 2, Y. If it, because this is a square, right?
Yeah.
On the bottom.
Yeah, so it's 2y. Yeah, I see that.
Yeah. So I'm thinking 2x, 2y, 0z for point D.
Okay, and then you subtract that from B to get the vector of
Yeah.
D. Okay, so you do. So it's 2, 2, 0 minus 0. Wait, 2,
0,
0,
0.
0.
Yeah.
So then the vector that finds D would be 0, 2, 0.
Yeah.
Okay.
I gotta find the. I'm gonna just Google like defining plane with 2 points in vector.
Has anyone done 2? Has anyone got a solution for number 2? Oh, great. You want to go write it up next to his solution for 1?
Atrocious.
Just write big. Mine can't be worse than mine, so thanks. Here's one solution for number 1 up on the board. Your solution can be correct, but might be different. There's lots of ways to write out that solution. And that's in vector form. It's not general form. We'll talk about how to go to vector to general form in a minute.
Yo, Post Malone, did you see my comment or whatever?
Yeah, I saw it. That was helpful. Thanks. So you get you get vectors by subtracting any point from any other point, and you only need two vectors, right? I think so. So if you get all the points and then just subtract them from each other, and then it works out pretty well.
Yeah, and I think the the T and the S and T could be any scalar because
Yeah.
you can get any point. So we didn't need to define them.
Yeah.
So I was off there. We didn't need to define them. So yeah. Yeah.
And this is a plane, not a line. So, okay.
Yeah. Okay. Do we want to do more?
I think I'm good. It makes sense to me. So.
Okay.
Kinda. I don't know, man.
Yeah, I agree.
Find the equation of the line of the origin that intersects K. So to find the line of E through B, that's pretty easy. That's just it's 1, 1, 2, and two, 0, 0.
All right. Okay, let's talk about these. So here we've got the 3 points listed, B, D, and E. The easiest, usually the vector forms are the easiest equations to find, because you can find the point and the vectors and you just write them in. If you're given something like a vector that's perpendicular to a line or perpendicular to a plane, then you want to go general form or normal form. The forms we work with most are vector and general form, just FYI. So here we have 3 points, and then this group, they found 2 vectors by taking B minus D and D minus E. So if you have points, how do you find vectors? You take a difference between points. So yes. So that question was, does it matter which one you subtract? Could you do D minus B and E minus D? It doesn't matter. As long as you get 2 independent vectors. So what you could not do here is take, like do B minus D and then do D minus B for your other vector, because those are just going to give you 2 vectors that point in opposite directions. And then as you scale, as you change S and T, you're just going to stretch these and you're just going to stay on a line. So you need to have what we call linearly independent vectors. Linear independence is going to be coming up in the next chapter. So yeah, but it doesn't matter which. Yeah, you can do B minus D, D minus B. Yeah, any combination of those subtractions, as long as you don't end up with a vector on the same line as the first one. So, okay, other questions? I thought there was another hand. Yes. And it also does not matter which of the 3 points you pick to be the point. That's right. So if you start out with some point in the plane, this says, hey, I'm interested in all the points that I can get by starting at this point and taking all possible lengths of these vectors and adding them together. And if you change this point, well, you're just going to change the lengths. You can, like, some combination of these could get you to this point, first point anyway, and you haven't changed much. So yeah, it doesn't matter what point you start with, and any 2 independent vectors in that plane work. So it doesn't matter which way you do these ordered. You could do a D, what are we missing? Like a B minus an E. You could use that as one of them. So yeah. Other questions? Okay. I know someone asked, how do you go to general form from this? Okay. So general form, we want to have a normal vector. Okay. We need a vector normal to the plane. So one thing that we can do is use the dot product and use these 2 vectors that we know are in the plane and find a vector that's perpendicular to the plane. We're going to find a vector that's perpendicular to both of these, and then it will be perpendicular to the plane. Okay? And to start off, I would just pick like ABC. So some unknown vector, ABC, and then dot it with that. and we know that has to equal 0. And then the vector ABC dotted with 1, 1, and negative 2 equals 0. And this will end up with, this will give us a system of equations. But this will be nice. This is really nice, this one, because I get 0 A's minus 2 B's and 0 C's. And so I get a minus 2B equals 0. So I know B equals 0. Okay. And how about here? I get A plus B minus 2C equals 0. And I already know that B has to be 0. So I do know that A minus 2C equals 0. But I don't have any more information. I can't solve exactly for A and C. So all I know is that A has to equal 2C. And I know B equals 0. So I can pick a value for A or a value for C. I can pick any value. What this represents is if I'm looking for a vector that's perpendicular to those, there's not just one vector that's perpendicular. There's lots of vectors that are perpendicular, right? I can stretch that and scale that vector. So there's not just one. So this kind of summarizes all of the vectors, all of the possible vectors that are perpendicular to these. I just need B equals 0 and A to equal 2C. So I could pick C equals 1, then I know A equals 2, and I can write down one vector. So pick C equals 1, then the vector is 2, 0, 1. So that's one vector. I only need one vector. And you can look, if we dot product with S, what do we end up with? 0, right? Because I get 2.0 is 0, 0.-2 is 0, 1.0 is 0. Nice. How about here? 2.1 is 2, 0.1 is 0, 1.-2 is a -2, and so I get 2 plus a -2 is 0. So it works. And now I can rewrite that. I know 2x plus 0, y plus 1, z equals some d. And then how am I going to solve for d? I can plug in a point. So I can pick any point. I've already got one here, 2, 0, 0. So I've got a point. If I plug in 2, 0, 0, I just end up with d equals 4. So 2 plus 0, 0 plus 1, 0 gets me 4. So d equals 4. So 2x plus z equals 4. This is the equation. That is the equation of this plane, same plane in general form. Okay. All right, any questions on that? Yes?
So I have the same logic, but I use different points. I took different vectors to find my original thing, and my answer is entirely different. Does it change based off the vector?
What is your answer?
1, -1, or x minus y minus z equals 2.
It can be different, but it can't be that different. It'll be a scalar. It has to be a scalar multiple of these. Maybe I made the mistake. So I'll come look at it. Okay. So, but yeah, you should get the same thing. In the last class, the example that got put up had different vectors, and we still ended up with the exact same plane. So yeah, so the question is, can it look different? It can look different. Because I could have picked this vector to be 4, 0, 2. And then this would have been 4x plus 2z, and this would have ended up being 8. So, but yeah, they will just be scalar multiples. Okay, other questions on this?
Yeah, quick question. So if you have 0, y, what does that mean for the point?
Nice question. It means that the y coordinate, no matter what the y coordinate is, you get the same, like x and z are the same. So basically, if you draw a line in the xz plane, this looks like the equation of a line, right? If we had x and y, right? So one way to think about this, let's say this is x, this is y, and this is z. If I have an equation in x and y, so I'm going to just think like 2x, I'm going to think easier. Y equals 3x plus 1. So it's going to be something like this in the xy plane. Then, but this is also the equation of a plane. And what it means is that like the plane will go from that line and go straight up and straight down, and there's no slant to it in the z direction. So it means something similar here, that if we were to draw this line in the xz plane at y equals 0, then we could just kind of stretch that out in the y direction. So, and I think that's what happens, right? If we, yeah, we're doing this plane right here. It slices the y, it slices, well, it's parallel. What's a good way to think about that? I don't know. Okay. Trying to think on my feet a nice explanation, but okay.
Basically, what that says is the plane is constructed of lines that are parallel to the y-axis. Is that all it's saying?
Yeah, that's a nice way to put it. I was trying to think of like parallel things, but yeah. So that plane is the plane can be constructed with lines that are parallel to the y-axis. I think that should work. So, okay, like here. Yeah, so here you could have lines. Any point on this could go up and down, and it could be parallel to z. So yeah, you could make that with lines that are parallel to the z-axis. So okay, how about let's do number 2 here. So number 2, we're finding the equation of a line. You know 2 points, E and B. You found EB, the vector that goes from E to B. So it's E minus, so they did B minus E. I think this is switched around, but they found a vector. And the way you create this is you take a point plus a vector, any vector in the line, the direction vector, or a direction vector times the parameter. This is back to a question earlier about what a parameter, when we talked about the parameter, what the parameter means. So we start with a point, and then we're just going to stretch this vector out, all possible stretches in whatever direction, in this direction. That's going to hit all of our possible points. 1 point for every t. So, okay, questions on this? Okay. Looks like we didn't get to the other ones. I will make a video that finishes going through this, so you can do those, especially 3. 3 is a little tricky. So there are different ways to do 3, but yeah, 3 is a little bit tricky. Have a great day. Homework's up on the board down here, over here on the right.